Hello and welcome to section 2.4, Derivatives of Trigonometric Functions. So when discussing these trigonometric functions, unless otherwise stated, we refer to a radian measurement, and all trigonometric functions are continuous at every number in their domain. So we could see here, if we let f of x be equal to the sine of x, we could see something interesting here when we sketch the graph of the derivative, right? We have at each time that we have each of the curves on our sine graph here is when we start getting those tangent lines with a slope of 0. And we could correspond that to this graph here on the bottom, which looks very similar to that cosine of x graph. But we could also pop it into our derivative formula to get that same result. If we put the limit as h approaches 0 of f of x plus h minus f of x divided by h, by putting in that sine of x in for each of those, this is the limit as h approaches 0 of the sine of x plus h minus the sine of x divided by h. And so, based on those trigonometric identities that we have, this is the limit as h approaches 0 of the sine of x times the cosine of h, plus the cosine of x times the sine of h, minus the sine of x. And we could break that apart, right? This makes this limit as h approaches 0 of the sine of x times the cosine of h, minus the sine of x divided by h, plus the cosine of x times the sine of h divided by h. So now, again, based on just factoring out in both of those, we have the limit as h approaches 0 of the sine of x times the cosine of h minus 1 divided by h, plus the cosine of x times the sine of h divided by h. And from what we know then about the limit, we could then break this apart a bit to get the limit as h approaches 0 of the sine of x times the limit as h approaches 0 of the cosine of h minus 1 divided by h, plus the limit as h approaches 0 of the cosine of x times the limit as h approaches 0 of the sine of h divided by h. So it turns out that just simplifies down to, well, the cosine of x. So with regards to that, the other trigonometric functions, the derivative of the cosine of x with respect to x is negative sine of x. The derivative with respect to x of the tangent of x is equal to the secant squared of x. The derivative with respect to x of the cosecant of x is the negative cosecant of x times the cotangent of x. The derivative of the secant of x with respect to x is the secant of x times the tangent of x. And the derivative with respect to x of the cotangent of x is the negative cosecant squared of x. So, what does that mean? Well, we could differentiate, in this case, x squared times the sine of x. So based on that product rule that we have, if we let u here be x squared, the derivative of u is 2x. If we let v be the sine of x, what we just saw, the derivative of v would be the cosine of x. So taking the derivative of y here, we would have x squared times the cosine of x plus 2x times the sine of x. And we can't really simplify that too much. You can take out an x, but not really going to simplify at all. The second example, I'm going to find the derivative of f of x is equal to 9x divided by 6 minus the tangent of x. So if we let u here be 9x, the derivative of u is just 9. If you let v be 6 minus the tangent of x, the derivative of v would be negative secant squared of x. So f prime of x is going to take 9 times 6 minus the tangent of x minus 9x times the negative secant squared of x. All divided by the denominator 6 minus the tangent of x squared. We could slightly rewrite this and factor out the 9. This would be 9 times 6 minus the tangent of x plus x times the secant squared of x. All divided by 6 minus the tangent of x squared. This third example. If an object is fastened to the end of a vertical spring is stretched 4 centimeters beyond its rest position, which we could see going on with this, and released at time t being equal to 0. Its position at time t is s would be f of t, which in this case is 4 times the cosine of t. We want to find the velocity and acceleration at time t, and then use them to analyze the motion of the object. So the velocity will just be that first derivative of f. So negative 4 times the sine of t. And the acceleration would be that first derivative of the velocity, or the second derivative of our original function. This would be negative 4 times the cosine of t. And you can see that periodic graphs up here based on our function. So the red one here's the position function, the blue one's the velocity, and the green is the acceleration between 0 and 2 pi. A couple of trigonometric limits, special ones, I should say. The limit as theta approaches 0 of the sine of theta divided by theta is just 1. And the limit as theta approaches 0 of the cosine of theta minus 1 divided by theta is equal to 0. So with this last example, we want to calculate the limit as x approaches 0 of the sine of 7x divided by 4x. So in order for us to do this, right before we actually do the limit, I want to rewrite that sine of 7x divided by 4x very briefly by multiplying both the numerator and denominator. In this case, by 7 divided by 7. Which is just like multiplying by 1 since the numerator and denominator are the same. We could rewrite this then as just 7/4 times the sine of 7x divided by 7x. So this limit is, I'm going to put the 7/4 in front since it's a constant. 7/4 times the limit as x approaches 0 of the sine of 7x divided by 7x. So if we were to let theta be 7x, then we could see then that the theta approaches 0 as x also approaches 0. Just multiply by 7. So this we could rewrite as just 7/4 times the limit as theta approaches 0 of the sine of theta divided by theta. And that would just give us 7/4 times 1 from that last slide. So that being just 7/4. Let me know if you have any questions or concerns. Thank you.